Right. So today we have a quiz. Simple harmonic motion and fluid part about Pascal's equation in Archimedes. Okay? Pressure is kind of blended into liquid pressure. Alright, so let's recap what we talked about last time. Yes?
So we said that Archimedes wasn't going to be on this quiz. I thought it was going to be like pressure fluid slash harmonic motion. Yeah. Density.
Yeah.
Yeah.
Okay. So liquid pressure and Pascal's equation. That's all I said? Yes.
Yeah.
Harmonic motion and pressure. Okay. No, elasticity. That's the one that we forgot. Okay. Elasticity, simple harmonic motion, and pressure up to Pascal. Okay? All right. So, last time we started talking about liquid behavior. We talked about how liquids create pressure on objects that are submerged in liquid. And we said that if I have a container that has a certain amount of liquid in it, then pressure at the bottom of this container is a very simple expression. It has to do with the density of the liquid times the G times the height of the liquid over that point. Okay, so this is common to all liquids, to an extent gases as well. Because gases are compressible, so it's a little bit different. But, you know, this is the pressure at the bottom. We also said that liquids have this ability to distribute pressure evenly throughout the liquid. And so I said if I look at the pressure on the sides at the same height, there would be exactly the same pressure. And if I had an irregular shape, the pressure at the same height at any point on that irregular shape would be the same given by this quantity here. Rho times G times the height of the liquid at that point. And the pressure would always be perpendicular to the surface of the liquid. So we said that takes us to a really neat principle, which is Pascal's principle. And it's the principle of all hydraulic systems. And that if I have a system of liquid and I arrange so that I have, let's say, two pistons created at the surface of this liquid, and I apply a certain amount of force here, that force will create a pressure within this liquid. That pressure that I've created here, which I call P1, is going to be F1 over A1, where the area is the area that I apply the force across. And that pressure very quickly will distribute itself to this liquid and will manifest itself on this piston here. So this piston adds a lot more area. So the force that I can support on this piston to balance this force, F2, would have to be consistent with the same pressure. So P2 must be equal to P1, okay, which means that F2 is equal to P2 times A2. And that means that if I look at the ratio of F1 to F2, so F1, so from here I have F1 is equal to P1 A1. So if I have F1 is equal to P1 A1 and F2 is equal to P2 A2, then F2 over F1 is equal to P2 A2 over P1 A1. But P1 and P2 are the same. That's a property of liquid. So I can cancel this, and I'm left with So I have a very large surface area here. The force that I can support is going to be proportionally larger. So that's why I can put a little bit of force here and lift the car at this end. Because I can make the ratio of those areas as large as necessary to lift the car. Okay, that's Pascal's principle. Okay? All right. So that's a very kind of a simple relationship here. You know, F2 over F1 is A2 over A1. So I give you on the quiz a problem that says, you know, I have a car that's 2,000 kilograms. How much force do I need to support it? If the area ratio is this, you should be able to tell me how much force I need to support it. If I say I have a car that's 2,000 pounds, I'm applying 100 pounds on this side. This area is, you know, 110 square centimeters. What should the area on this side be? You should be able to figure it out. If I say I have a car that's 2,000 pounds, I'm supporting it with an area of, you know, 1 square meter. I'm applying the force. That's 100 pounds here. What is the diameter of my piston? You'll be able to figure the area and then the diameter, right? Diameter is simply, so area is equal to 5 d squared. All right? So, we would look at this problem and say, how many different ways could he possibly ask? Make sure that you can solve all those possible ways. Okay. Then the next thing we talked about was Archimedes' principle. Archimedes' principle is a really neat thing. Again, it's all out of this pressure thing. It basically says that if I have an object that is submerged in a liquid, okay, there will be a difference in pressure on this object, right? There's going to be pressure here and a pressure here. This pressure here depends on this height, H1 let's call it. This pressure here depends on that height, H2. Okay? Obviously, since H2 is larger, the pressure from the bottom is going to be larger. Okay? The pressure from the large bottom is larger. That means there's an imbalance. There's a net imbalance in pressure. That means there's a net pressure upwards on this guy. And we derive what that, how that pressure manifests itself into a force. And we said the buoyant force, S of B, is equal to rho, the density of the liquid, times G, times the volume of the object. Another way of saying this is that the force on a submerged object is equal to the weight of the liquid displaced. So, if you look at this, you will see that the volume of the object is the volume of the liquid displaced, right? And then rho of the liquid times the volume of the liquid is the mass of the liquid displaced, times G is the weight of the liquid displaced. So this is weight of liquid displaced. Okay? So, then the next thing was, what if this buoyant force is more than the weight of the object? So if I have an object, it has some weight also, right? mg. And then there's the buoyant force, has to be equal to that. What if this buoyant force is more than the weight of the object? Then the object is going to try to go up. It's going to try to float, right? It's going to go up to the surface. The minute it starts poking its head above the surface, the volume of the liquid displaced is going to get smaller. So the buoyant force is going to start going down, and it's going to go up, 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 until the buoyant force equals the weight, and then it's going to stop. And so the corollary to Archimedes' principle, so this is Archimedes' principle, this one, corollary, is that a floating object displaces an amount of liquid amount of liquid equal to its weight. Or the weight of the liquid displaced is equal to the weight of the object for a floating object. Okay? Alright, so that's basically what Archimedes' principle is and employs Archimedes' principle. So, yes, sir.
So you're saying it gets smaller as it goes towards the top because there's less liquid displaced as the object goes up?
Once it starts poking above the surface of the liquid, that's when buoyant force starts going down because then there's less liquid being displaced. As long as it's fully submerged, the amount of liquid displaced is the same as the volume of the object. But once the object starts poking above the surface, then the amount of liquid displaced is whatever is below the surface, right? And so it starts going down, and so the buoyant force starts going down, and then when the buoyant force equals to the weight of the object, then it basically stops going up, and that's when we say it's floating. Okay? So, this is the principle by which, fish swim every day. When they have little air sacs in their body. When they, fill that air sac with air, their volume increases, but their weight does not. So they displace more water. Therefore, the buoyant force is increased. Therefore, they go up. When they squeeze the air sac down, their buoyant force goes down. They sink. Same thing with submarines. Submarines have these giant chambers, if you will. When they fill those chambers with water, they sink, and then when they blow the water out with the compressed air, their density goes down, and they float. Okay? So, really neat stuff. Any questions about Pascal or Archimedes?
Did you say that the weight of the liquid displaced is the weight of the floating object, or equals the weight of the floating object?
That's correct.
Oh, thank you.
Floating object displaces an amount of liquid equal to its weight. Or another way of saying it is that the weight of the liquid displaced is equal to the weight of the object for a floating object. Okay, so Thursday we're going to do an experiment on the Archimedes principle. And we're going to do essentially what Archimedes did to figure out whether the stuff that the king got was gold or not. Okay? We're going to have objects that we're going to weigh outside. Okay? Or we know the weight of. And then we're going to weigh them when it's submerged. Okay, so we're going to have a scale. We're going to tie a string to the scale and weigh the thing submerged. What submerges it? Okay, and vary the mass, generate a graph. From the graph, get actually, from the slope of the graph, you get the density of the object. And if, for Archimedes, for example, he did the same thing for what the king had, and did the same thing for pure gold that the king had, and compared the densities and said, oh, not the same density as gold, you got screwed. Okay. All right? Okay, so I'll go over this. I'll send you the stuff tonight or tomorrow morning. I should send that over the weekend, right? You guys didn't have it. Oh